How's it going, Algebra 2? This is not Algebra 2. How's it going, statistics students? So used to recording Algebra 2 videos. This is Mr. Shack with your Chapter 4 review video. Again, as always, going to be going kind of fast to make sure I can get everything or try to get everything in within the 30 minutes that I have because the video just cuts off after 30 minutes. So ideally, I'm going to try to get this all in. These first ones go kind of fast, so hopping right into it right away. Um, if you're talking speeds, right, and again, we're looking whether these variables would be considered discrete or continuous. If you're talking speeds, you're saying like, is it just like 1 mile per hour, 2 mile per hour, 3 mile per hour, or whatever, or can you be between? And is that continuous? And yeah, you can be between. It's not just like whole number mile per hours. Although that's what we usually see, this would be continuous. I'm going to go C for continuous, D for discrete. Number of cheeseburgers, okay. If you're talking about what they're serving, I suppose if you're talking about what you're eating, you could have like 1.5 or 1 1/4 cheeseburger, but they're serving whole cheeseburgers, so they serve either 1, 2, 3, 4, or and so on. Okay, I wrote a 1. That's D for discrete. Okay, the number of people who play the state lottery each day. Again, you can only have whole number people, so that's discrete. Okay, only whole numbers of people. The weight, if you're talking weight, that can be continuous, right? You can weigh 136.7 pounds or whatever. Okay, the time it takes to complete a marathon. Again, time. Time is going to be continuous, right? Because it's not just, hours. There's hours, minutes, seconds. You can even break seconds down into milliseconds and so on. Number of mathematics majors, again, we're counting the number of math majors. Those are people. You can't have half or parts of people. Okay, blood pressure, that's continuous. Again, that's something you can measure. That is not just whole numbers. Okay, so hopefully those aren't too bad. If we're talking for any discrete probability distribution, the sum of all associated probabilities must be equal to, okay, if you're talking any probability, always, or any probability distribution, sorry, it should always add up to equal 1. Always. Okay, so then you're looking at this and you're saying, well, does this represent a probability distribution? So you're looking at your P of X, right? Your P of X is your probability. So let's add these up. Do these equal 1? They add up to 1.1. So no, that can't be a probability distribution, right? Because they have to add up to 1. And that's what you would explain. I'm not going to write that out. Hopefully you can hear me. You should be listening to this if you're watching this for any other reason, just to check your answers. You should be listening to my explanation. Okay. Uh, Number 4. Okay. Which of the following is not a property of binomial experiment? Okay. Again, that is the BINS criteria that we talk about. Okay. Should have n fixed numbers of trials, right? This is your n. There are exactly 2 outcomes. That's the B for binary. The individual trials are dependent on each other. This would be false, right? So that is the one that is not. That would be false because they need to be independent, not dependent. That's the I. Okay, and then the probability of success, same for each trial. That's the S and the BINS. Okay, again, this is wrong because it's saying dependent. It needs to be independent. Moving on. Okay, here we have an expected value problem. We've done a good amount of these, I feel like, so hopefully this is somewhat fresh up in your brain still. At a raffle, 10,000 tickets are sold, $2 each. Okay, there's 3 prizes valued at $2,400, $1,200, and $500. What is the expected value of 1 ticket? Okay, well, let's just set up our table first. Remember, X is always your gain, right? So that's your gains. Remember, you're spending $2 on each ticket, so you're not actually winning 2,400. You're winning. I gotta sneeze. Yeah, excuse me. You are winning 2,400. Yeah, but you're spending $2 on the ticket. So really, your gain there would be 2,398. Okay, and then same here. You got to subtract 2 from this because you'd really be winning 1,198. That's the 1,200 minus 2, and then 498 for the 500. And then, okay, those are the three ways you win, right? But then most of the time, more often than not, you're not winning a raffle, which means you're gaining -2, right? Because you're spending 2 on the ticket, because it is $2 for the ticket. And now we're saying, like, well, what's the probability you take home this or you gain this amount each? Well, there's only one top prize, right? And that's 1 out of 10,000. Okay, there's only one second prize. That's another 1 out of 10,000. Okay, because there's 10,000 total. And there's only one third place prize, and that's another 1 out of 10,000. Okay, and then, well, the rest of the people, they're just spending $2 on the ticket, not winning anything. That's the whole thing with raffles, right? You're trying to give yourself a chance to win $2. Most people look at that as nothing, right? You're just giving yourself a chance. But more often than not, the majority of people, everyone besides 3 people, will just be wasting $2, right? So you can think of 10,000, subtract these 3. You subtract 3 from 10,000, that's 9,997 out of the 10,000. That's how many people are just throwing away $2, right? Just because they wanted to give their chance to take home one of these prizes. Okay, so now when you are finding expected value, you are multiplying x times px, or x times its probability, right? So x times its probability, and then adding that all up. So what that will look like is you're going to have 2398, okay, times the 1 over 10,000. Okay, and essentially when you're doing this, it's really just going to become like, because this is like over 1. So you could write this as 2398 over 10,000, and I could go, and then you're adding all these, right? So I'm saying plus 1198 over 10,000. Again, that's just because that's what happens when you multiply top times top, bottom times bottom. And then you go on and say, well, plus 498 over 10,000. Again, that's the same as saying 498 times 1 over 10,000. And then lastly, this one I'll write out because it's a -2 times 997 over the 10,000. Okay, be careful when you're putting that in your calculator. So make sure you are separating all these with addition signs. And as long as you do that, you should be good. Your calculator knows PEMDAS for the most part. Sometimes it can't read your mind. So if you're saying like plus a -2 times 997 over 10,000, I would put that in parentheses, like put your fractions like this in parentheses, because otherwise it might do your order of operations incorrectly. However, if you do put that all in, for the sake of time, I'm not putting it in. But if you do put that in correctly, you should get -1.59, which means the expected value, if you're playing this, you would expect to lose on average $1.59. Okay, that's how something like that would be done. If you did not get this and you need help, but like, what did I do wrong? How did I put this in my calculator wrong? Please just talk to me. Talk to me in class. Okay, as we go down to 6, we are given a distribution again, and we are finding the mean. Okay, and it tells you the formula right here, mu. So the mean is sigma x times p of x. Okay, so the sigma tells you are adding. That tells you are adding x times p of x for each of these. So that's 5 times 0.2. Okay, sigma says add, right? So 6 times 0.25. Again, add, times 7 times 0.38, plus 8 times 0.1. Okay, and then lastly, I ran out of room. We'll go down here, plus 9 times 0.07. Again, as long as you just do 5 times 0.2 plus 6 times 0.25 plus 7 times 0.38 in your calculator like that, you should have no problem. Like you can put it in just like that. Your calculator will know what you're talking about. And you should get 6.59, which I would say go ahead and round to 6.6. If you left it at 6.59, that's fine. Just making it one decimal place will make this part go a little bit faster for you. So when you're finding the variance now, and again, the formula is given to you, you are saying x minus mu. Well, mu is what we just found, right? X's are all of these squared times p of x. So let's just get this started. And our first x is 5, right? That's our first x minus the mu that we just found, which is 6.6. Okay, and that is squared, it says. So you're just, as long as you know how to use this, you're fine because I give you formulas. So times p of x, well, the p of x for that is 0.2. So times 0.2. Okay, and then again, the sigma tells you you're going to continuously add that. So now I again add, and I'm on to the next column. Oops, you can't see, sorry. I'm on to the next column. So I'm now saying 6 is my x minus mu. Well, mu is not changing, right? That's 6.6 still. That's the mean that we found in part 1. Again, squared, because this tells me so, times p of x. Well, p of x for 6 is it's 0.25, not 0.25. So times 0.25. Okay, on to the next one. So I'm saying plus. I'm running out of room because I'm writing way too big, but we're just going down here onto the next column. So I got 7 minus 0.3, oops, sorry, minus your mu, which is 6.6, my fault, 6.6 squared, and now it's times your probability 0.38. Okay, on to 8, so it is 8 minus your mean, which is 6.6, that's squared, times its probability, which is 0.1. Okay, finally, one last one, we have 9. We're on 9, right? 9 minus your 6.6, your mean, right? That's squared. Okay, times the probability there, the p of x, which is 0.07. Okay, again, put this in your calculator exactly how it looks, and you'll be fine. If you do the 5 minus 6.6 in parentheses, squared, like close your parentheses and then square it, then times it by 0.2 plus, and then again, just put it in exactly how we wrote this. If you put this in your calculator exactly how you wrote it with parentheses and all, your calculator will know what to do, and you should get 1.262. Okay, that's what you should get here when you add all that up in your calculator. All right, number 3. Well, this was the variance, right? You just found sigma squared, your variance. So to find the standard deviation, you just take the square root of that. So the square root of 1.262 tells you to round to the nearest tenth. You should get 1.1 when you round. Okay, moving on. Number 7, we have a student takes a 20-question true-false exam, guesses 1 each question. Okay, so they're guessing either true or false each question. Find the probability of passing if the lowest passing grade is 15 correct out of 20. Would you consider the event likely to occur? Explain. Okay, use your graphing calculator to solve. That means we're probably using our binomial CDF or PDF. So let's look at this. We got 20 questions, right? That tells me that's my fixed number of trials, right? N is 20 for the 20 questions. They're guessing either true or false, right? So they actually have a 50% chance of guessing each question right, as well as a 50% chance of guessing each question wrong, right? Because it's either true or false. It's one or the other. So just like a coin flip, that's a 0.5 success rate. Okay, that's your probability of success, 0.5. Probability of passing if the lowest passing grade is 15 correct out of 20. That means that's the lowest you can get. So x, you're saying what do you need? X has to be greater than or it could equal 15. Okay, so x is greater than or equal to 15. So we have NPX, right? Those are the 3 things we need to be able to use our binomial function in our calculator. Now, here's the thing, right? I say you always have to have this pointing to the left. Right now, it is not. So I'm going to have to change this, right? Let's just make a little arrow. And it's going to be a 1 minus. Anytime you're having to change it and it's greater than type of question, well, then you're going to have to change it and just say 1 minus. Now, do the opposite of greater than or equal to. So opposite of greater than is less than. Opposite of equal to would be not to have that equal to. So we are less than 15, right? So 1 minus x less than 15. Okay, again, if you're thinking, well, how'd you get the x greater than or equal to 15? I went kind of fast past that. But the lowest passing grade is 15 out of 20. Okay, so that means 15 is the lowest you can get, and then anything above 15, you're good. So x has to be greater than or equal to 15. Have to change that to pointing to the left. So you do 1 minus, since you're changing it to pointing it to the left. X less than is opposite of greater than, and then it's not equal to. Since this was or equal to, this one cannot be equal to. So then what am I putting in my calculator? Again, don't forget the 1 minus, because we had to change it here to point to the left. So it is 1 minus binomial. Is it an exact one? That tells you whether it's CDF or PDF. Since this is not like x equals this, it is, you are counting, right? So that is CDF, right? You're only using PDF if it said like exactly 15 correct. If it was exactly 15 correct, then you'd use PDF. It is not exactly 15, so you are using CDF. Okay, and then always NPX. So N we found to be 20 for the 20 questions. P, that's your success, probability of success, that's 0.5. And then X, here's the thing, right? We're saying X has to be less than 15. Well, if X is less than 15, it cannot be 15. So you're putting in a 14 for X, okay? You're going to the one less than 15, which is 14. So this is NP X. I will show you how to put this one in your calculator. We got a bunch of these coming up on 8. I'm not going to show you all of them in the calculator. I'll just show you this one in the calculator, and then I'll set them up for you, but hope that you can do that. So again, to get there, you're going second vars, right? Second vars. You can't see my calculator. I'm going to go over like this, okay? So I hit second, and then I go vars, which has the distribution above it, which is why we're using that one. I'm looking for binomial CDF. Okay, there it is, binomial CDF. That's what I need. Okay, and then we already set it up for ourselves. It's always n, comma, p, comma, x. So always npx. So n is 20. I hit my comma, which is right here. Okay, p 0.5, comma, x is 14. Okay, I can close my parentheses, honestly. If you don't, you'll be fine. Hold on, though. Did I forget something? I did forget to do the 1 minus, right? This is a 1 minus because we had to switch it to less than. So I can still hit enter there, but now I need to remember I'm going 1 minus, and I'm doing 1 minus that answer. So that will work for me that way, but otherwise, I probably should have remembered that right away and gone 1 minus and then go into the second var as binomial CDF. I can save myself by remembering to do it here because I did 1 minus my answer, which will give me the same thing. Okay. So what did we get? We got 0.021 when we round, which that is 2.1%. Okay, that's their chance of passing. That is very unlikely. So is this event likely? No, we would say unlikely, and the number speaks for itself, right? Unlikely because it's 2.1% chance. That means about 98 out of 100 times he's going to fail. So way more often than not he's failing. Okay, if we go on to 8, we have 1 in 4 adults currently on a diet. In a random sample of 8 adults, what is the probability that the number is currently on a diet is, and then they give us these following numbers. So again, these are going to be your binomial distributions again, where you're saying, okay, 1 in 4 adults currently on a diet. That is your probability that they're on a diet. That's 1 out of 4. In other words, 0.25, right? 25% of adults on a diet. Random sample of 8 adults, that's your fixed number. N is 8. Okay, and these are giving you your x's that you're going to use. So you got NP. Now the only other thing you need is your x. Okay, what is the probability that the number currently on a diet is? Exactly 5. And again, you know this is binomial. You can check this with your BINS criteria, right? There's 2 outcomes. They're either on a diet or not. Each adult is independent of the other. N, fixed number of trials, right? We got 8 adults, and then the probability of success, probability that they're on a diet is 1/4 for every adult, right? Because 1 in 4 adults. So that does pass the criteria, which means we are on to this for exactly 5 Exactly 5 means x has to equal 5. Okay, so when it's equal, I can use binomial PDF, right? That's only time I'm using PDF is if it's an exactly. So if it's an equal, exactly 5. And then it's NPX, right? N is 8, P 0.25, and then X is this 5. Okay, so we got NPX. You put it in exactly like this. Second vars, find binomial PDF, 8, comma 0.25, comma 5. You should get 0.023. Okay, going down to B for less than 5. If we're talking less than 5, that's x less than 5. We are pointing to the left. Always got to keep it to the left, right? So remember Beyonce, I think it is, to the left, to the left. If that helps you, yeah, this always needs to be pointed to the left. Okay, for less than 5, well, now it's not exactly anymore. So now I know I'm using binomial CDF. Okay, so I use CDF. Again, N and P aren't going to change for any of these. It's 8, comma 0.25. Now your X is what's changing. If we're saying less than 5, well, less than 5, it can't be a 5 here. Less than 5 would be 4. So I have to go 1 less than 5 whenever I see this. So think if it's X less than 5, it cannot equal 5, right? So that's when you go 1 less. Okay, you put in, again, second vars, binomial CDF, and then go 8, comma 0.25, comma 4, and you should get 0.973. Okay, that's what you should get there. If you go to C, and we are now talking at most 5. At most 5, think about that. That means it's 5 at the very most or less than 5. So that's less than or equal to 5, right? In this case, it can equal 5. So very similar to this last one, but now it's at most 5, so it can equal 5. Again, it's not an exactly, so if it's not an exactly equal, it's always CDF. So please realize that. And then again, NPX, well, N is still 8, P is still 0.25. X now, if it's less than or equal to 5, you have a 5 for X. Okay. Now when you put this in, you should get 0.996. Okay. I'll do this last one in my calculator. Again, it's a more than 5, right? And I'll show you the calculator steps in case you didn't catch it on the first one. But more than 5 now, that means X has to be greater than 5, right? X has to be greater than 5. Well, again, remember, got to keep this to the left. So if it's not to the left, you got to change that, which means we're going to end up going 1 minus. Okay, so don't forget that. If we're changing it, it's going to be 1 minus. And then we got to get it to the left. So I'm changing it to the left. That's the opposite of greater than. And then this one does not have equal. So this one needs that or equal to line. Okay, let's then are equal to 5. Okay, so then when I'm putting this in my calculator, I need to remember to go 1 minus binomial. Again, it's not exactly, it's got a inequality. So that's how I know it's CDF still. And then N is still 8, P is still 0.25, and then your X, it's less than or equal to 5, so it is 5 here. Okay, when I go in my calculator, I am saying 1 minus, I'll do that right away this time. I forgot to last time on number 7. So 1 minus, and then I go second vars. I go down to binomial CDF. I go 8, comma, 0.25, comma, 5. Close parentheses, enter, and you should get 0.004 when you round, 0.004. Okay. That's how you are doing those types of problems. I got to keep going kind of fast here because I think I might be running out of time on this video. Hopefully not. But as I go down to 9, 43% of adults in the U.S. receive fewer than 5 phone calls a day. On a random sample of 7 adults, okay, that tells me right away, I'm going to point that out. We got 7 adults. What is the probability that the number receiving fewer than 5 calls a day is exactly 3? We're looking for what the probability is that X equals 3 is what that's telling me. 43% of adults, that is my probability. So probability is 0.43. Okay, that's my probability. So now again, this does pass your BINS criteria, right? So you are going to the binomial, in this case, x equals 3, exactly 3, right? Exactly 3. That's when you're using PDF, as if it's ever exactly. Okay, and then it's NPX. So think NPX, always your N, we got 7 adults, right? For P, that's the probability. 43% of adults in the United States receive fewer than 5 phone calls. So that's the probability, 0.43. And X is 3, right? We're finding it for exactly 3. Put it in your calculator exactly like this. Make sure you go second vars binomial PDF, not C this time. And you're going 7, 0.43, 3. You should get 0.294 when you round. Okay. On to the last page. The last page. Here we go. Rolling the dice. Okay, a die is rolled 360 times. A die. So we're rolling one die. It's saying find the mean, variance, and standard deviation of the number of fives. Okay, number of fives is what we're looking for. That would be rolled. Okay, you're given the formulas for each of these. So for the mean, it is n times p. Well, n is your trials, right? N is 360 for the 360 times. Okay, well, there we go. 360 times p. P is the probability of success, probability of rolling a 5. Will that be 1 out of 6, right? 5, there's 1 5 out of the 6 possible outcomes on a die. So it's 360 times 1/6. That's really the same as doing 360 divided by 6, and that's 60. Okay. Well, then variance again, NPQ. So that's 360 times 1/6, right? Because the NP we're just stealing from up here. Now Q, that's your failure. Failure would be rolling anything but a 5. Anything but a 5 is your other 5 out of 6, right? So now I'm saying times 5 out of 6. When we do that, you should get 50. It's NPQ. Okay, standard deviation, just the square root of NPQ. So take your square root of 50, and you should get about 7.07. Okay, on average, how many 5s will be rolled? Well, that's the mean, right? The mean is your average. We said 60. 65s will be rolled on average. If you rolled it about 360 times, you'd expect to roll about 60 5s, 60 of each number. Okay. You observe the gender. So now in this one, we're just identifying N, P, Q, and X. So really, this is easier than what we were doing on the last page because we're not having to put it in. But this is really like half the battle. You got to find what N, P, and X are, and then you can put it in your calculator. In this, we're just finding N, P, Q, and X. Okay. So you observe the gender of the next 100 babies. Okay, that's your N. N is the 100 babies you're observing. You count the number of boys born. Okay, identify the values of N, P, Q, and X. Probability that it's a boy born is 1 out of 2, right? It's either a boy or a girl. So that's 0.5 that it's a boy. This is your success because you're looking for boys. So having a boy would be a success in this case. And then, well, failure, right, would be in this case having a girl. So, and it's 0.5 for each, 50% for each, right? And then your X's, well, they can have 0 boys, they can have 1 boy, they can have 2 boys, they can have all the way up to 100 boys, right? So this is what it's looking for X's. You're just listing those out, those possible outcomes. Okay, for 25% of the people in the U.S. with internet access go online to get news. Okay, 25% of people. So this is your P. So P is 0.25, right? That's 25% of people. Random sample of 5 Americans with internet access is selected, and if they get their news online. Okay, so 0.25 of them do, which means 0.75 of them don't. Okay, so this is the yes, this is the no in this case. Let's see, a random sample of 5 Americans. Okay, 5 Americans, that's your N. That's your sample. That's your fixed number in this case. And then your possible outcomes, right? You got 0, 1, 2, 3, 4, or 5. That's it there. Okay, I know I went really fast on this last one, especially, but I think I'm about out of time. Please let me know if you have questions in class, and good luck on your test.